we're given that 2 cosec squared x equals 5 minus 5 cot x, and we're told to show that this form can also be written in this form. And basically you've already started this question, but essentially we have 2 cosec squared x equals 5 minus 5 cot x. I don't know why, I just like writing out the stuff again. It just makes it more clear in my head. Well, cosec squared x is actually an identity that you kind of have to remember, but I'll just go through it anyways. So we have cosec squared x, and that's the same as 1 over sine squared x. With sine squared x, my mind immediately just jumps to the identity sine squared x plus cos squared x. Well, what does this equal? Obviously this equals 1. That's the original trigonometric identity that we were taught in year 11 or year 12. So basically from here, because it's 1 over sine squared x, I kind of know that I'm going to have to divide everything by sine squared x. So I get this becomes 1, and 1 over cos squared x over sine squared x, and this equals 1 over sine squared x. Okay, so luckily it's already in this format. And so we can say cosec squared x equals 1 plus, and sine squared x, cos squared x over sine squared x is actually just 1 over tan squared x. So you can just say cot squared x. And now that we have this identity, we can see that 2 cosec squared x is actually equal to 2 lots of this. So 2, 1 plus cot squared x, 5 minus 5 cot x. And now it's just a matter of expanding this out. So 2 plus 2 cot squared x equals 5 minus 5 cot x, and then so 2 cot squared x plus 5 cot x, and then the 2 minus the 5 equals minus 3 equals 0, which is what this equation is here. Cool. So part B says, hence so show that tan x equals 2 or tan x equals minus a third. So in this format, what we asked to do, so let's go about solving this. So we have 2 cot squared x plus 5 cot x minus 3 equals 0. And then from here, it's just a hidden quadratic. So let's say y equals, let y equal cot x. So 2y squared plus 5y minus 3 equals 0. I'm assuming you know how to factorize, because if you don't know how to factorize at this point, then that's a bit crazy, but anyways, so this becomes 2, 1, 3. I like doing this method here, and this is the cross method. So this becomes 2y minus 1 and y plus 3 equals 0. So y equals 3.5. So minus 3.5. So now that we have that, so y equals cot x. So cot x equals minus 3 cot x equals 1/2. Cool. So we asked to show that tan x equals 2, tan x equals minus a third. So obviously tan x would therefore, let me make it in pink, just make it colorful just because why not? So tan x equals minus 1 over 3 and tan x equals 2. And that's it, because cot is just 1 over tan. Cool. So that's part B. And then part C, hence or otherwise solve the equation 2 cosec squared x equals 5 minus 5 cot x, giving all the values of x in radians to 1 decimal place in the interval minus pi is less than x, which is less than or equal to pi. Part A and part B means that we've done the majority of the question for part C. So tan x equals minus a third and tan x equals 2. Wait, what was it again? Yeah, minus pi and is less than x, which is less than or equal to pi. So the first thing I do for questions like this is I just kind of like to just sketch it out. And I like to sketch it out because it allows me to see what kind of like answer this is going to be. So tan, obviously it's the funky one where it goes like this and it goes like this. Because we're only working in terms of minus pi and pi, we only need this aspect and this aspect up to here, and that's what I've drawn. Minus a third is going to be somewhere like here, and then 2 is going to be like somewhere up here, let's just say. So there's going to be 2 values for 2 and 2 values for minus a third. Cool. So now that we know that, so tan x equals minus third, x equals tan inverse of minus a third. Where's my calculator? So the tan inverse of minus a third equals minus 0.32175 And essentially, because we know that tan repeats every pi degrees, what am I saying? Tan repeats every pi radians. So this second value is going to be plus pi 2.8198. So therefore, those are the two values for minus a third. So when x equals tan inverse of 2, x equals, so tan inverse of 2 is going to equal 1.10715, and then the other one is going to be minus pi. So minus pi is going to be minus 2.03444. Cool. So the four values of x are therefore going to be x equals minus 0.32. I just like doing three significant figures most of the time. 2.82, 1.11, and minus 2.03. I don't know why this 3 is disconnected. Cool. So those are the four values of x. So as we notice, most A-level questions are going to be like this. They build you up. So they help you. Part A and part B actually helps with part C. And as you can tell, like, they kind of lead from one another. So one question leads to another question that leads to another question. Like a really hard question, they could ask this. They probably won't. They'll just be like, oh, solve this equation given this. Initially, we don't know what we need to do, but as you can see, these steps show you what you need to do. So to begin with, convert it into this format, because what is this? This is just a hidden quadratic, and with that hidden quadratic, we get something a lot more simple to just solve. Cool. So the next question, we need to show that the equation 2 cot squared x plus 5 cosec x equals 10 can be written in the form 2 cosec squared x. Again, it's just the same thing. We just need to convert this. So yeah, so we have this question now. The thing about this question is the same thing, same concept as the question that we did earlier, but in the opposite format. So as we found out earlier, 1 plus cot squared x equals cosec squared x. Well, this is an identity that should be as common to you as sine squared x plus cos squared x plus equals 1. And then from there, we need to understand that we just need to rearrange this so that this is 2 cot squared x equals cosec squared x minus 1. So because we know that, that just becomes 2 cosec squared x minus 1 plus 5 cosec x equals 10. Okay, so that is 2 cosec squared x minus 2 plus 5 cosec x equals 10. And now we just need to rearrange. So 2 cosec squared x plus 5 cosec x, and then minus 12, because we're just minusing 10 on both sides, equals 0. And that's what they have there. Perfect. So part B, or part II, we need to hence show that sine x equals minus a quarter and sine x equals 2/3. So it's the same thing again. So sine x equals a quarter, or was it 2/3 again? Yeah, 2/3. So we just start from there again. So we have 2 cosec squared x plus 5 cosec x minus 12 equals 0. So again, it's the whole process of a hidden quadratic. I'm not going to do the y equals, let y equals, because we already know this. So 2, 1, and then minus 12 is going to be 4 and minus 3. Cool. So we have 2 cosec x minus 3, and we have x 2 cosec x plus 4 equals 0. So cosec x equals 3 over 2 or minus 4. So a sec x, so sine x equals 2 over 3 or minus 1 over 4. Perfect. Okay, now part B finally. So I'm just going to copy and paste this over just because I don't want to write this down again. So now we're doing part B. So hence or otherwise solve the equation 2 cot squared theta minus 0.1, and that, well, we've already solved most of this because we know that sine x equals this. So all we're going to have to do is, instead of x, we just put in theta. So sine theta minus 0.1 equals 2/3 or minus a quarter. So then from here, all we need to do is, and it's in the range minus pi, theta, and pi. So again, like the same thing earlier, I like sketching this out. So yeah, so the first thing I'm going to do is just sketch this out. And the reason why I sketch this out is because it just allows me to see what the values are going to be. Yes, we know that there's 2 values here and 2 values here. Cool. So now that we do have that, we can just say sine theta minus 0.1 equals, and then 2/3. So theta minus 0.1 equals, or sine inverse of 2 over 3 gives me 0.72997. And then the other value is going to be pi minus that. So pi minus answer equals 2.41186. And then when sine theta minus 0.1 equals minus a quarter, so inverse sine of minus a quarter equals minus 0.25268. And then the other value is going to be pi minus that. So pi minus answer minus pi plus answer equals sine inverse of minus a quarter. So it's minus pi minus answer, which equals minus 2.8889. Cool. So the 4 values of theta, because as you can see here, there's going to be 4 values. So theta minus 0.1 equals 0.729. Let's just say 0.730, 2.41, 0.253, minus 2.889. Or let's just do 2.89. I just like 3 significant figures just because it's just always ingrained in my brain to do that. So theta is therefore going to equal, theta equals 0.830, 2.51, 0.353, minus 2.99. Cool. So those are the 4 values of theta. So the next question, rabbits were introduced onto an island. The number of rabbits t years after they were introduced is modeled that's crazy, modeled by the equation p equals 80, e to the power of 1 over 3t, where t is a real number and it's greater than 0. So we need to write the number of rabbits that were introduced onto the island. So to begin with, because when t is equal or is greater than or equal to 0, obviously the first number of rabbits is going to be when t equals 0, right? So that's the initial time. So how many rabbits were introduced? Well, eat anything to the power of 0. So 1 over 3 multiplied by 0 is just going to be 0, and anything to the power of 0 is 1. So 80 times 1 is going to be 80. So the initial number of rabbits is going to be 80. So we need to find the number of years it would take for the number of rabbits to exceed 1,000. So that's super simple. We just know that this is just a simple exponentials question. 80 1 over 3t equals 1,000. So when is this going to be 1,000? We can do this a multitude of ways. I kind of just using learning on both sides. So first of all, I'm going to divide by 80. So 80 1 over 3t equals 1,000 divided by 80, and then learning both sides. So it's 1 over 3t equals ln of 1,000 over 80. So t equals 3 ln 1,000 over 80. And this equals 7.577. So the number of years is going to be 8. It's going to be 8 years. So C, we need to find dp by dt. So to begin with, what is p? So p equals 80 e to the power of 1 over 3t. So how do we differentiate this? So this differentiated is relatively simple. It's just the chain rule. So what is the chain rule? So yeah, the chain rule is actually just super simple. At the end of the day, I feel like most students are like, most teachers overcomplicate it to begin with. more than anything else. But the main thing about the chain rule is we use it when there's a function inside of a function. So yeah, the chain rule is super easy. We just find the differential of this and then multiply by the differential of this. So, well, what's at e to the power of third dt differentiated? It's just the same thing. So at e to the power of 1 over 3t, and this is going to be multiplied by the derivative of this. So the derivative of that is just a third. So the answer is going to be at over 3 e to the power of 1 over 3t, and that's it. So find p when dp by dt equals 50. So part D, when at over 3 e to the power of 1 over 3t equals 50. So we just do e to the power of 1 over 3t equals 150 over 80. So 1 over 3t equals ln of just this. I'm just going to do that because I don't want to write it again. So t equals 3 lots of that. So this equals 3 ln 150 over 80. And this equals 1.886. Okay. And obviously we're not done yet because we need to find what p is. So p equals e to the power of e to the 80, 1 over 3 to the power multiplied by 1.886, and this equals my answer. That gives me 150. So the population comes to 150. That's such a nice number. But yeah, cool, lovely, nice. So figure 8 shows the curve y equals f of x, where f of x equals 1 minus x e to the power of 2x with its turning point p. So the turning point is there. We need to write down the coordinates of the intercepts of y equals f of x with the x-axis and the y-axis. So we need to find the exact coordinates of the turning points p. So the exact coordinates of the turning point p. So that's the first thing we need to do. Obviously we're only doing part I and part II. So the first part is write down the coordinates of the intercepts of f of x and x-axis and the y-axis. So the x-axis is when it touches 0, when y equals 0, and this is when x equals 0. So when y equals 0, we have 1 minus x e to the power of 2x equals 0. So the first one is x equals 1, and the second one is when e to the power of 2x is 1 equals 0. Well, obviously e to the power of 2x can never be 0, so the only time this is going to be 0 is when x equals 1. So y equals 1 minus 1. Oh, well. Lol, that's going to be 0. So the coordinates of the x-intercept is going to be 1 and 0. Cool. And the next one, we have x equals 0. So y equals 1 minus 0 multiplied by 1, because e to the power of 0 is 1. So y equals 1. So the two coordinates are 0, 1, and 1, 0. Very nice. Okay, so we need to find the exact coordinates of the turning point p, and it's this value here. Let's just call this y. So dy by dx, we need to find when this equals 0, because what a turning point is when it changes direction, and at that point the gradient, as you can see, is 0. So we need to find the exact coordinates of the turning point. So to begin with, what is y? Y equals 1 minus x e to the power of 2x. So here we need to differentiate this. And as you can tell, there's two things being multiplied together, and there's also the chain rule in that sense. So to begin with, we have u dash. So what's u? U is 1 minus x. What's u dash? Minus 1. V, which equals e to the power of 2x. What's v dash? V dash equals 2e to the 2x, because it's the differential of this. That's chain rule. So this times that, and this times that. 1 minus x multiplied by 2e to the 2x plus v, which is e to the power of 2x to the power of multiplied by minus 1. So this just becomes negative. Cool. So we have 2e to the 2x minus x times 2e to the 2x minus e to the 2x, and this all equals 0. So yeah, so from here, essentially we know that everything's in terms of e to the 2x, so we just put this together. So you have e to the 2x 2 minus 1 minus 2x equals 0. So e to the 2x, and then 1 minus 2x equals 0. So x equals a half is when this equals 0. So what does y equal when x equals a half? So y equals 1 minus 1 over 2 multiplied by e to the 2 times a half. So this equals a half times e, and I'm just going to leave it like that actually. So the turning point is going to be when the coordinates are this, when x equals a half and y equals a half e. So as we can notice, most A-level questions are going to be like this. They build you up, so they help you. Part A and part B actually helps with part C. And as you can tell, like, they kind of lead from one another. So one question leads to another question that leads to another question. Like a really hard question, they could ask this. They probably won't. But like once you get into university and stuff like that, they'll just be like, oh, solve this equation given this. Initially, we don't know what we need to do, but as you can see, these steps show you what you need to do. So to begin with, convert it into this format, because what is this? This is just a hidden quadratic, and with the hidden quadratic, we get something a lot more simple to just solve. Cool.